Hi grade 12s and welcome to this video. In this video, we're going to be working on Eastern Cape's April 2021 math control test. So this one is a short paper. It is 50 marks and the time allocated to this paper is 1 hour. Okay, so let's get into the paper. So, question 1.1 says the following geometric sequence is given. And as you can see, we have 10, 5, 2.5, 1.25. And this is what the question says. Calculate the value of the fifth term 5, okay, of this sequence. So they're just asking for the fifth term. But I want you to notice that this is only for 1 mark. So this is just a one-step process. It's not something that's supposed to take long, meaning we don't need the TN formula. So to calculate the fifth term, this is what you're going to have to do. You see, this is the first, the second, third, and fourth term. Think about this. This is a geometric sequence, right? So it means when we have the first term, because it's geometric, we multiply the first term by something to get the second term. Then we multiply the second term by something to get the third term. Now we need to find out what exactly that thing is. What is that number? And that number is regarded as your common ratio. So if you find the common ratio, you'll be able to find the fifth term. How do we find the common ratio? The common ratio is found by saying term 2 divided by term 1. So if you say term 2 divided by term 1, that simplifies to a half. So now we know the common ratio is a half. So it means that term 5 would be found by saying term 4 multiplied by a half. Okay, term 4, which is 1.25, multiplied by a half, and that would finally give you term 5. And that answer is 5/8. Okay, moving on to the next question. Question 1.1.2 says, determine the nth term Tn in terms of n. So they're asking you for the Tn formula, which is just the general formula. Remember that this is a geometric sequence. So the Tn formula of a geometric sequence is Tn is equal to A multiplied by R raised to the power of n minus 1. So what is the value of A? Well, we have that. That is the first term, which is 10. So we can say Tn is equal to 10 multiplied by our ratio we found in the previous question is a half raised to the power of n minus 1, and that is our answer. Moving on to the next question. So the next question is 1.1.3, and the question says explain why the infinite series, and then this is what we have, it's the same series that we have, the same sequence. You need to explain why it exists. Okay, so here's the thing about this thing existing. It is an infinite geometric series, right? The fact that it is infinite, as you can see, we have plus dot dot dot. The only way it can be infinite is if it keeps on going infinitely and doesn't actually end. Okay, that's what geometric series do. I know we can calculate the sum to infinity of it, but that's the thing. We're calculating the sum to infinity, meaning it doesn't end. For us to say that this series exists, it would have to do what we say, converge. The series would have to converge. And for a series to converge, this is what must happen. Its constant ratio needs to be greater than -1, but smaller than 1. That's what you do when they ask you to explain why a series, an infinite series, exists. So clearly we just need to put the common ratio in between, okay, which is a half. So a half is greater than -1 but smaller than 1, and we know that is true. A half truly is greater than -1 but smaller than 1, and that is why it exists. So you can conclude, therefore, the infinite series exists. Okay, moving on to the next question. Okay, so question 1.2 says the sum of the first p terms of a sequence of numbers is given by this equation. And they want us to calculate the value of term 20. Okay, so this is a question that has shown up, but it has not shown up in a while. So let me explain it on a smaller scale so that you can understand this one. Let's say I said, let's find the sum of 3 terms. This will be made up of term 1 plus term 2 plus term 3. And what if I said, okay, let's also find the sum of two terms? This will be made up of term 1 plus term 2. Now, look at what we can actually find here. If I said the sum of 3 terms minus the sum of 2 terms, I want to see what's going to be left. If I'm taking the sum of 3 terms, meaning everything here minus everything here, look at what would cancel. Term 1 would cancel with the term 1. The term 2 would cancel with the term 2. And do you see what you're left with? Term 3. So it means that if you wanted the third term, you just need to say the sum of 3 terms minus the sum of 2 terms, and you would find the third term. So likewise, here, if we wanted the 20th term, right, term 20, we should just say the sum of 20 terms minus the sum of 19 terms, and then we will be left with the 20th term. Okay, so that's what we're going to do. So let's go ahead and substitute. Term 20 is going to be equal to the sum of 20 terms. So every time you see P, right, you're going to replace that with 20. So let's go. That's going to be 20 multiplied by 20 plus 1 multiplied by 20 plus 2. And we need to take this and subtract it by the sum of 19 terms. So every time you see P again, replace it with 19. So we're saying 19 times 19 plus 1 times 19 plus 2. And now we can just go ahead and put that onto the calculator. And we get 1,260. So that is the 20th term. Okay, moving on to the next question. Question 1.3 says we have to evaluate this. So you see that we have the sum starting from k being equal to 1 till infinity. So this is the sum to infinity of this pattern with the formula 1 over 3 raised to the power of k. Then we have this, which looks very different, but it's still a series. It's a series that is being subtracted. We're minusing by the series. But this series starts from where k is equal to 2 and ends at 40. And it's a series of 5. 5 just keeps repeating throughout that series. 5 keeps being added. That's actually what's going on. So we can go ahead and expand the series so that we can understand it better first. So the first series is the sum to infinity, but you see that it starts at k is equal to 1. So to find the first term, you would substitute 1 in place of k over there. So if you say 1 over 3 to the power of 1, you just get 1 over 3. Then to get the second term, substitute 2. So 1 over 3 to the power of 2, you get 1 over 9. Third term, substitute 3. 1 over 3 to the power of 3, you get 1 over 27. So that's the series here, right? Then this one, the series that we're going to have for that one is going to be like this. Remember, it's just a series of 5, but starting where k is equal to 2. Okay, so this series is just a repetition of 5 that keeps being added. So we're just going to have 5 plus 5 plus 5, and this keeps going. Okay, so in this one, we can clearly see this is the sum to infinity because there's an infinite amount of terms here. So that one would not be so bad to figure out. We can actually find that. You can just say, okay, this is the sum to infinity, right? And you can find what that is. The formula of that is a over 1 minus r. So we know what that is. Our a value is 1 over 3, and then 1 minus our ratio. If you divide, you can already see what this keeps multiplying by. It keeps multiplying by 1 over 3. But if you say term 2 divided by term 1, you'd get 1 over 3. Term 3 divided by term 2, you'd also get 1 over 3. Okay, so we know how to find that. But how do we find the sum of this? Well, first of all, remember that it starts where k is equal to 2 and it ends at 40. So let's think about how many sets of 5 kept being added. Okay, and this is really where you're trying to find out how many terms do you have in this series. Okay, what are the number of terms? It's not 40. You must never just look at that and say, oh, it's 40, because this starts where k is equal to 2. Just like if I had a series like this, if I said the sum where k is equal to, let's say, 0 and ends at 5. If I asked you how many terms are there in the series, it's not 5. It's actually 6 because you have k is equal to 0, k is equal to 1, k is equal to 2, k is equal to 3, 4, and 5. That's actually 6 terms. So when k does not start from 1, the number that you see on top is not the amount of terms. Now there's the formula to find the amount of terms. To find the number of terms in a series, you just say the top number, okay, where you end, you can say end minus start, and you add 1 to that. So this is the number that you end at, this is the number that you start at. So we would say 40 minus 2 plus 1, which gives us 39. So it means there are actually 39 terms here. So think about it. How do we know how much all of this would be when added together if we know there are 39 sets of 5? If there were only 3 sets of 5 and I said calculate the sum of this, you could have just said, oh, okay, there are 3 sets of 5. So 3 times 5 instead of saying 5 plus 5 plus 5. Likewise with this, you can just say the sum of that, okay, sum of the 39 terms would be 39 multiplied by 5. Okay, so with the sum to infinity, we already know what that formula is. So we're just saying the sum to infinity, right? This is what this is telling us to do. Take the sum to infinity and then subtract it by the sum of these terms, which is 39 terms. So I'll say sum to infinity minus the sum of those 39 terms. And so this is the calculation for the sum to infinity. We can go ahead and just put that on the calculator. So I'll put a fraction first, then I'm saying 1 over 3. Then on the denominator of that fraction, I'm saying 1 minus 1 over 3, which I get 1 over 2 as my answer. So the sum to infinity here is just 1 over 2, right? And minus the sum of 39 terms, which is 39 times 5. So 39 times 5 is 195, and so minus 195, and a half minus 195, let's just find out what that is. And our answer, you can put it as a decimal as well, just leave it as a decimal, is negative 194.5. So if you just want to be precise with them, you can show them the series that they gave you in sigma notation, that minus that is equal to negative 194.5. Okay, so moving on to the next question. Okay, so we are in the last question for question 1, which is 1.4, and it says, Atlehang generates a sequence, which he claims that the sequence can be arithmetic and also geometric, if and only if the first term in the sequence is 1. And they're asking, is he correct? And you need to motivate your answer by showing all calculations. Okay, so let's focus on his claim. So he generates a sequence and then he claims that this sequence, it's one particular sequence. That's one thing we need to just remember. The sequence is the same thing. That sequence, right, can be arithmetic and geometric at the same time. If and only if the first term in the sequence is 1. Okay, so we need to show them that this is actually true. So in other words, we're trying to find a sequence or trying to prove to them that there is a sequence that exists that is both arithmetic and geometric, but the first term has to be 1 for this to happen. Okay, so since we have two sides, let's try to think about this. First of all, the sequence that we're speaking about must be the same thing, right? It's one single sequence. But this sequence is both arithmetic and geometric. So what I'm saying is that they will look exactly the same as the sequence, but they're both going to be arithmetic and geometric, which really just means that in the arithmetic one, let me actually just put 2 columns for arithmetic and geometric. Okay, so we have 2 columns for those. In the arithmetic and the geometric one, right, that these 2 sequences, which is really the same sequence, just remember that in an arithmetic sequence, you have an A value, the first value, which we know is 1 now, right? Then we don't know what the second term is. We don't know what the third term is in that sequence. But in an arithmetic sequence, how do we find each term in the arithmetic sequence? Well, you can use the T-end formula. At least we know what the first term is. in an arithmetic sequence. Or you could use this method. So feel free to use the arithmetic TN formula, but you can also use this method. Since we know an arithmetic sequence works like this, the first term is A. The second term, right, we find by actually saying, it's not a series, it's a sequence. So second term we find by saying that first term plus something. It's plus the constant difference. So the second term would be A plus D. And then of course the third term, you would again take the second term and add D to it again. So the third term would be A plus 2D. Okay, that would be the arithmetic sequence. And likewise with the geometric, you can also use the TN formula, but you could also think about it like this. The first term is A as well. And then the second term we find by saying the first term multiplied by the constant ratio, which is A multiplied by R is AR. Okay, so I just need to put semicolons. And then to get to the third term, again, you would multiply by R. That's AR squared. Okay, so that's what we'll keep doing to keep getting all our terms. But the thing is, they told us what A was. They told us what the first term is. The first term is 1. So let's replace A with 1 in all of these. So it means our arithmetic sequence looks like this. It says 1, then the next term is 1 plus D, and then the next term is 1 plus 2D. Then the geometric one would look like this. It's 1, then we have AR, so that's 1 times R, which is just going to be R. And then we have 1 times R squared, which is just going to be R squared. So these are what our sequences should look like if they are arithmetic and the first term is still 1, and geometric and the first term is also still 1. But here's the thing about it. What Atlehang is claiming is that the sequence can be arithmetic and also geometric, the sequence, meaning this sequence is the exact same sequence. What that would mean is that its first term should be exactly the same, which we can see they are the same in both the arithmetic and geometric. But that also means that the second term should also be exactly the same. Okay? And also further, it means that the third term should be exactly the same. Let me change that to a lighter color. For us to actually prove that this sequence exists, okay, that it's both arithmetic and geometric, if it's arithmetic, it must have a what? It must have a constant difference. And if it's geometric, it must have a constant ratio. So clearly this is a situation where we're going to solve for D and R, and then that D and R value is going to be the values for which this sequence is arithmetic and geometric at the same time. Okay, so remember it is the same sequence, right? So this is what is being used to tie everything together. It's the same sequence. So the first term and the first term should be exactly the same. And the second term and the second term should be exactly the same. So I'm going to have an equation where I'm going to actually equate them because I know they should be the same since they're the same sequence. So term 2 should be equal to term 2 in the geometric sequence. Term 2 in the arithmetic is 1 plus D. Term 2 in the geometric is R. Okay, so this is all we have. Can't really do anything with that. I mean, R is a subject. So let's equate term 3 now. So term 3 should be equal to term 3 in that. So I'm going to say term 3 being equal to term 3. And let's see what we get. We're going to say 1 plus D, 2D, is equal to R squared. Okay, now these are two equations that we got from these. And D and R in both equations stand for the same thing. So the equations are connected. So I can call this equation 1, and I can call this equation 2. And this is a simultaneous equation now. So how about we just substitute, because since R is the subject nicely here, how about we just substitute equation 1 into equation 2, and that will help us to solve for D. Then we can solve for R. So if we can actually have a D and an R value, then it would mean that yes, he's actually right. A sequence can exist if its first term is 1. Okay, so let's substitute equation 1 into equation 2. Okay, substituting equation 1 into equation 2. So equation 2 says 1 plus 2D is equal to r squared. You see, equation 1 is the equation for r. So wherever you see r, replace it with 1 plus d. So 1 plus d all squared. Okay, so we just have to do some simplifying here. So this is going to be 1 plus 2d being equal to, and you can go ahead and FOIL this out like that. That takes long. I use a simpler method where I square the first term. That is just going to be 1. Then I say first term times second term. 1 times d is d. Then you take that and you multiply it by 2. So it means we have positive 2d. Then lastly, square the last term. That will be positive d squared. Okay, so this is what we have. You can start taking things over. Like, for example, if you take 1 over, it will become negative. If you take 2d over, it will also become negative. And you see that they will cancel with these ones. So what I'm seeing is I have a positive 1 and a positive 2d. They will cancel on both sides. Meaning, on the left-hand side, I'm left with 0 is equal to d squared. Okay, then to find d, you can square root both sides. And so d is finally just equal to 0. So our common difference must be 0. Okay, what must the ratio be for this to happen? Well, if you like, you can go ahead and call this equation 3. Then just substitute equation 3 into equation 1 to find r. So equation 1 is r is equal to 1 plus d. So if r is equal to 1 plus d, but we know d is now 0, r is equal to 1. So yes, these are actual values. We have a value of d, we have a common difference, and we have a constant ratio as well. So this just means that the sequence actually does exist as long as the first term is 1. So we can actually claim that yes, he is correct, that it can actually happen. Okay, so therefore he is correct. And sorry, just to add to that, let me actually write out the series, what it's going to be. That series would be, so let's just look at it on both sides. We know what r and d are supposed to be. If d is 0 here, it means you're not really adding anything, right? So it's 1 plus 0, which is 1, plus 0, which is 1. So that stays 1, 1, 1. And then do you see here with the constant ratio, you keep multiplying by the ratio. But if r is equal to 1, then 1 times 1 is 1. And 1 times 1 is 1. So that sequence must be this. So I'll just say the sequence is 1, 1, and 1. And that just keeps going. Okay, moving on to question 2. 2.1 says, in the diagram below, triangle PQR is given such that QT is 3 units, and I'm already going to just be checking and filling in. So QT is 3 units, TV is 5 units, TR is 8 units. So TR is 8 units, right? And they tell us that ST is parallel to PV. So these two lines are parallel. The first question is determine the following with reasons. And we have to find QS over PS. So let's see what QS is. So they want QS, right? And look at the line that is parallel there. So QS, meaning this side is going to be in line with this side. Over PS, which is this. And so that means that this side is in line with this side. So do you see the ratios that belong to it? So it means that QS is equal to PS because of this. And I'm really going to have to say it like this. QS over PS, sorry, not is equal to, over, is equal to, so the QS, that ratio, it will take whatever ratio is there. That is 3, but that is a length, over 5. So the reason I said it will take whatever ratio, I know that this is a side, but the thing is in this one, these lengths happen to be lengths that didn't really simplify with each other. 3 and 5 don't have anything in common. So either ways, even if this was like 6 and 10, 6 over 10 would have still given you 3 over 5. The numbers that they gave you just don't simplify, but please don't mistake these numbers as ratios. They're actually the length of these lines. They just happen to also just not simplify. Okay, but you're going to have to give a reason. So we did that really. That's because of the proportionality theorem. But the reason that we give is because there's a line drawn parallel to one side of the triangle. Also, with that being said, you need to put these ratios here. And this is where that is actually very important. you see, because this is 3 over 5, I can call this 3a and this one 5a. The reason I'm saying 3a and 5a is because it is not the length of the side, it is just the ratio. It is just how these are being shared. For example, the actual length of this side could have actually been 6, and the actual length of this side could have actually been 10. And if you put them over each other, they would give you 3 over 5. That's what I mean by that. Okay, so that is there. Let's move on to the next question. Question 2.1.2 says we need to find the area of triangle PQR over the area of quadrilateral PSTR. So let me highlight those. So PQR is that bigger triangle and PSTR, that quadrilateral, is that yellow one. Because you can see that we do not have a perpendicular height in any of these, we are going to be using the area of a triangle, but the trigonometry version of that. So if you have a triangle and you've been given this angle, let's say you've also been given this side and this side. So you must be given the sides that are right next to that angle, right? What you can do, let's just name this ABC. To find the area of this shape, you can say a half multiplied by one of the side, which is AB, multiplied by the other side, which is AC. Then you say sine of angle A. Now, in this question, because we are clearly dividing these quadrilaterals, they need to divide over each other, right? And since they need to divide over each other, you need something to happen here. So looking at the triangle, the area of PQR, look at PQR, right? Do you see that you have PQ, the side PQ? It's in terms of ratios, but at least we have something there. PS, we have nothing here. We can't really do that. So you have PQ, you also have QR, and we have this Q. We may not have the angle, but that's not a problem. And this is where we have to think about how to find the area of this quadrilateral. If we're going to use this as the center angle, right, for this triangle, since you have this side and this side, what you're going to have to do when you're finding this quadrilateral is this. You're going to have to try and find the area of this quadrilateral in a way that it's going to include this angle. Okay, because at the end, we always say sine of that middle angle. So you're going to have to find the area of this quadrilateral in a way that it's going to include sine of angle Q. So for that quadrilateral, let's think about that. Since we're looking at the quadrilateral, how can we find that in a way that it's going to include sine of angle Q? Well, what if you took the entire area of this big triangle, right? That's PQR, and then you subtracted it by the area of this little triangle on top? What will you be left with? The quadrilateral. So that's what we're going to do there. So we can write a construction of how we're going to do this. The area of triangle PQR, we'll just say the area of triangle PQR, right? That's how we'll find that one, just by actually finding the area of that. But for that quadrilateral, we're going to have to take the area of this bigger triangle, triangle PQR. So we're going to take the area of triangle PQR, but then we're going to have to remove from it the area of this triangle on top, that smaller one, which is triangle QST. So minus the area of triangle QST. And that will get us to that quadrilateral. Okay, so let's go ahead and calculate. So this is equal to, let's find the area of triangle PQR. So because we have this side and this side, we start off by saying a half multiplied by the one side, and you can see that QP is made up of 3A plus 5A, which is 8A. So a half times 8A multiplied by the other side. Now this other side is not ratios, they're just lengths. So QR is made up of 3 plus this total TR of 8. So 3 plus 8 is 11. So plus 11, that one is just a number. Then we say sine of the middle angle, the angle that is in between these two sides, which is angle Q. So we're going to say sine of angle Q. And you will see how sine of angle Q will cancel. And that's why we try to make sine of angle Q included in all the calculations that we have. And then we have area of triangle PQR, which is exactly the same thing. So we can just rewrite it. So minus the area of triangle QST. So that is minus the calculation of the area as a half times 1 of the side QS, right? That small side is just 3A. So times 3A multiplied by the other side QT is just 3. So actual length of 3. And then we say sine of the middle angle, which is angle Q. Okay, so let's just look at this and see how we can simplify. The numerator, we just have a half times 8, which is 4. And then 4 times 11 is 44. So what we have there is 44A sine of angle Q. And then on the denominator, what we'll have is, again here, this is the exact same thing. So we'd also have 44A sine of angle Q. Then we subtract this by, so as you can see, we have, I'm just going to say 3 times 3 first is 9. And 9 times a half is 9 over 2. A sine of angle Q. So do you see that these are like terms? They're in terms of A sine of angle Q. We can subtract those. So on the numerator, we still have 44A sine of angle Q. And on the denominator, we can find out what 44, because this is just the like term. Find out what 44 minus 9 over 2 is. And as a fraction, that is 79 over 2. So 79 over 2. And so it's also still going to be in terms of its like term, which is A sine of angle Q. Okay, so now that we have this, do you see that A and A would cancel? Sine of angle Q and sine of angle Q will cancel. And all you're left with is 44 being divided by, and I'm writing it as a division sign now, over, right? Divided by 79 over 2. Then you can just actually punch this on your calculator. And our answer is 88 over 79. And that is what that answer gives us. Okay, so that is it for question 2.1.2. Moving on to the next question. Okay, so now we're on question 2.2, and 2.2 says, in the diagram, a circle with a tangent CD, right, is drawn. Then we have A, B, D, and E are points on the circumference of the circle. Then they tell us that AE is equal to AB. So that is equal to that. AE and AB are equal. And we have that AB is parallel to ED. So those two lines are parallel. Then they also tell us that angle A1 is equal to X. So let's actually just put that down. That is X. Okay, so now we have the first question, 2.2.1, give with reasons 3 more angles equal to X. Okay, so let's just see. So 3 more angles equal to X. Look at where X is. X is at the circumference. But also remember we have parallel lines. So I can see that we have a Z here for alternate angles. So if this is X, this is also going to be X. Okay, so we can just tell them that angle D3 is equal to angle A1, which is equal to X because of alternate angles on parallel lines are equal. Okay, and I just like to specify the lines that are parallel. So now we know that this is also X. Okay, where else do we have X, or should we have X? So I'm still remembering that this is at the circumference and we had a tangent, right? So if this is a tangent, the angle between the tangent and the chord is equal to the angle supported by that same chord at the circumference. So it means that angle D1 being the angle between the tangent and the chord is also going to be X. Okay, so angle D1 is equal to angle A1, which is equal to X because of the tan chord theorem. Okay, so already have X there. What else? So we have 2 places now that we have X, 1 and 2. Where else? Do you remember that they told you that AE is equal to AB, right? So do you see that the angle supported by AE, that chord AE, is this angle D3, which is equal to X. If you have a chord that is exactly the same length as well, also supporting another angle at the circumference as well, then they should be equal in length because equal chords would support equal angles at the circumference. You see, because they have the same length of a chord, they would support the same size of angle at the circumference. So it means that this is also X. So we can just go ahead and tell them that angle D2 is equal to angle D3, which is equal to X, because of equal chords supporting equal angles at the circumference. Okay, so that's what we have there. So that's the first question, and that is done. So just make sure that you have X in all the places that it should be. So that's what you would be doing in an exam setting. Make sure you leave it there because it will probably help you with the next question. Moving on to the next question. Okay, question 2.2.2 says prove that triangle DEA is similar to triangle DBC. Okay, let's go ahead and highlight those triangles. So triangle DEA is DEA, and then DBC is this triangle here, DBC. How are those similar? Okay, so for them to be similar, we need all their angles to be equal. Or you could also look for the sides, but as you can see, they didn't really give you the length of the sides. Like we don't know this is 8 centimeters, for example. So we're looking at the angles. Well, good thing is angle D3, do you see that is X? And in that triangle, angle D1 is also X. So we have one angle at least down, 2 more to go, or really just 1 more to go. If you get one angle, then by default, the third angle in both triangles will be equal. Okay, so in order to find this, we can think about the order in which they named it. The order is very important. It actually tells you how they're going to be equal to each other. They said D, E, A, right? So D being the X, the one with X, then E, and then A. So name that triangle as well like that so that you can see what angle is probably equal to what angle. So that is DBC, see, with the X, then B, C. Okay, so let's think about that. How can we make this be equal to this? But I can already see that, you see, since point A, B, E, and D, they lie on the circumference of the circle, then this is a cyclic quadrilateral. And so do you see that this is the exterior angle, it's the angle outside the cyclic quad. This is the exterior angle of a cyclic quad, so it's equal to the opposite interior angle. So there, we know now that those two are equal, and we know why. Now we just have to state everything that we have. And so because those two are equal, because these two are equal, by default, it means that this angle must be equal to that angle because it's the third angle in the triangle. A triangle can only add up to 180 degrees, so these two would by default be equal. Okay, so I can start off by saying in triangle ADE and triangle DBC, so DBC, then this is what we have. First, we had the x's being equal because they were just proven already. So I can go ahead and tell them that angle D3 is actually equal to angle D1, and that was proven. I can further also say that they're both equal to x, okay? And this has been proven. Next, we have that exterior angle. So that is angle B2 is equal to angle E because of the exterior angle of a cyclic quad. And lastly, that would make the two third angles in the triangle equal. So angle A2 by default is equal to angle C. So we can just put that down as well. Okay, so since we have those three being equal and I changed this is DEA, I wrote something else. Okay, so we can conclude that triangle DEA is finally similar to triangle DBC, and this is because of angle, angle, angle. Okay, moving on to the next question. Okay, the next question, 2.2.3, says we need to prove that A, first of all, we have DC is equal to BC multiplied by AD over DB. So every time they give you something like that, after they've asked you to prove that two triangles are similar, it's usually coming from the proportions of these triangles. So this is how we can use these proportions. So we don't necessarily need the actual diagram to show them how they are in proportion. We can just use the lettering of what we have here. So you're going to take the sides over each other. The first side we'll take is DE. And you see I took the first and second letter. So in the second triangle, I'll also take the first and second letter. So I'm saying that it means that DE, right, over DB should be equal to EA over BC. See? Second and third. So that's EA over BC. And this should be equal to lastly, the last two. So DA, or you could call that AD. So DA but they called it AD here. So AD over DC, and they also have DC there. So these are the proportions because we have similar triangles. Those triangles are in proportion in this way. So now that we have this, what we can do is we can look at this, right? Because this just came by cross multiplying and stuff. So we can look at this and see what sides do we have here that are here so that we know which proportions to use. It usually needs to be 2 by 2 like that, or those two, or even the first and the last. So let's see which proportions we need to use. Do you see that first we have DC? We also have DC here. Then we have BC, and we also have BC. We have AD, we also have AD. The only thing it seems like, okay, we also have DB. So that's usually not supposed to happen. It's supposed to be one pair together. So it means that there's probably something we need to look into here. Okay. So it's supposed to either be this one with this one or this one with this one. So let's try and find out, where did EA, what is EA equal to? Because it might be a situation where EA is actually equal to DB, and then we can replace DB in place of EA, and then all the sides that we have here will be here in our two proportions. So let's go and check EA out and see how is that happening. What is it equal to? So EA, if we look at EA or AE, so AE is this one line here. The only other thing it's equal to is AB, which we are not trying to replace it with AB because that question that they asked that had nothing to do with AB. You see, there's no AB here. So EA. But do you now see, look at that. You see, you have a triangle and you have X here and X here. This is an isosceles triangle. So it means that you have two angles equal, therefore two sides would be equal. So since you have that being equal, look at the side that will be equal. It's the side that is opposite your equal angle. So it means that AB should be equal to BC. But remember, we were looking for AE, but that's not a problem because now we already knew before that AE was already equal to AB. But now we're seeing that AB is equal to BC because this is an isosceles, because this is an isosceles triangle. So do you see now how AE is actually equal to BD because of this isosceles triangle? So we need to neatly write that down for them. We need to tell them that first. Okay, so I know which proportions I'm going to take now. I'm going to take these two. They're okay. They're working out. So I'm going to therefore say EA over BC is equal to AD over DC. Then I'm going to tell them what I found out. I found out that since these two are equal, right, that it means that BD is equal to AB. So we tell them that. So since angle A1 is equal to angle D2, which is X, it means that those two lines are equal, that AB is actually equal to DB. And then you have to give a reason for this, okay? So normally it's a situation where you have a triangle and then two sides are already equal, right? Then you have to show them, oh, okay, then those two angles are equal. And the reason for that would be angles opposite equal sides are equal. But this time we see that the angles are already equal. So you can just say sides opposite equal angles are equal. Okay, so it's really just the opposite of that one. Okay, so now that we know they are equal, we can now replace. So also just tell them now, because remember, this was coming from EA. We found out that since AE or EA, right, and AB were already equal, and now we know that DB is also equal to AB, then it means that these two lengths are equal. So that's what we're just concluding. So therefore, it means that AE, and I'm just going to call it AE in alphabetical order. So AE is finally equal to DB, and that's good. So now we can finally take this that we had, and then in place of AE, EA, that's AE, in place of that, we're just going to put DB. So this therefore means that, so we have AE, so I put DB instead, over BC is equal to AD over DC. Okay, now to get it to look like this, it's just some multiplying we're going to need to do. So let's cross multiply first. So cross multiply, and we're saying BC times AD, that is BC times AD, and then DB multiplied by DC, multiplying across. Then you see that here, DC is the subject of the formula. So we just have to get DC to be on its own, and then everything will work out. So how do we get DC alone? By getting rid of DB. So since they're multiplying, you get rid of it by dividing. So divide both sides by DB. And so now we can finally say that DC, right, because it's left, that's the only thing there, is equal to BC multiplied by AD over DB. And that is what we have here, as you can see. Okay, so that is A of question 2.2.3 for 3 marks. Moving on to the next question. Okay, then 2.2.3b says we need to prove that EA is equal to DC times DE over AD. We still have repeated letters again. So I'm going to actually use that triangle, but also just remember the things that we have proven here, like the fact that those two are equal, things like that. Okay, so I'm going to use these proportions again because clearly they are repeating some stuff from here. Okay, do you see that in this question? Look at the proportions that they have here. They have EA, which is here, right? But we also know what it's equal to as well. They also have DC and they have DE, which is here. But we know that AE and DB are equal, right? And you see that they have AD as well. So the only other thing that I don't have highlighted here is this AE, which I know is equal to DB. So that's not a problem. Okay, so clearly in this one, they're just using this proportion and that proportion. So we're just going to go ahead and tell them that DE over DB, right, is equal to AD over DC. And you can tell them it's from the similar triangles that you had, right? And so to make sure that we have everything, you just see that we know that AD and DC are fine. We have those, and DE is also okay. We just have to tell them about DE and EA. Previously, we showed them that AE was equal to DB. So we can already tell them, but we know that AE is equal to DB. Okay, and this was proven already. So in place of DB, just replace DB with AE. That's all. So we're just going to say that, therefore it means that DE over, and I see DB, I will replace that with AE. Over AE, that's why they have EA there. Let me just keep it in their order. EA is equal to, and again, we just have AD over DC, which was fine. So we just needed to look like that. Then you can just cross multiply again. So cross multiply, EA times AD is just EA times AD, which is equal to DE times DC. And now that we have that, all we can just go ahead and do is try to make it to look like this, meaning just make EA the subject. So let's make EA the subject by dividing both sides by AD so that AD comes out of that left-hand side. So it means that EA and AD cancels is equal to DE multiplied by DC over AD. We can compare that to what they have. Do you see that? We have exactly what they have, just our DC is before our DA. You can, if you like, put it in that same order. So you can put the DC first, multiplied by the DE. Okay, so they're just playing around with these lengths. So that is also for 3 marks. Okay, moving on to the next question. Okay, and then the last question, hence prove that AE squared is equal to BC times ED. Okay, AE squared. I'm happy to see AE squared because I know that DB, right, was equal to AE. So if I like, I'll just call DB, wherever I see DB, I'll just call it AE, and then I will have 2 sets of AEs. So again, it seems like they're using the proportions of that triangle. So if I pull down those proportions, let's see what they have. So you see the proportions, we have BD here and we have AE here as well. And we know that those two are equal and they had AE squared. So we're just going to replace DB with AE. So clearly in this one, we're using the first and the second proportion. So they're really just playing around with the proportions. Okay, so as you can see, you have BC, we're going to take BC. You have ED, we're going to take ED, right? But then you have AE squared, and that's not a problem because here we have AE, and we know that DB is also equal to AE. Okay, so there we can just take these two proportions. We're telling them that DE over DB is equal to AE over BC. And this is, of course, from the similar triangles. And then we can finally tell them, but we know that AE is equal to DB. So wherever you see DB, replace it with AE. So this means that we have DE over, and in place of DB, we put AE is equal to AE over BC. Then just cross multiply. AE times AE is AE squared is equal to, and let me just try and put it in their order. They said the BC first and then the ED second. So I'm just going to say cross multiply. That's BC being multiplied by DE. And there, again. So they're just playing around with those proportions. So that is a whole 5 marks that you could gain there because they were not complicating it. Okay, so that is it for question 2. And then we move on to trigonometry in question 3. Then finally, question 3, which is the last question for this paper. It says, in the diagram below, we have a reflex TOP. So TOP, that reflex angle, is equal to alpha, and we have P is a coordinate, which is -5 and -12. First question, we have to determine the value of each of the following trigonometric ratios without using a calculator. So we need to find cos of alpha. So when they put down a point, we can go ahead and complete our triangle. So from that point, we will draw a line up to the x-axis, and it's perpendicular to the x-axis. Then let's fill in the adjacent, opposite, and hypotenuse. So because our coordinate is -5 and -12, -5 is an x value, -12 is a y value. The x value is just like normal coordinates. The x values would go from left to right. So it's going to be on here. That's your x value of -5 that we have, right? It's a coordinate, x coordinate. And then the y value, -12, you see, that's what's going to be here because it's saying this is a y value on the y-axis of -12. So we have -12 here. So now we have to find the radius. So let's find the radius first. And we're going to use Pythagoras. So the radius, or the hypotenuse squared, is always going to be equal to the one shorter side squared, which is the -5 squared, plus the other shorter side squared, which is the -12 squared. Okay, then we can say r squared is equal to, and you can just punch that into your calculator, and we get 169. Okay, then you need to solve for r. So you'd square root both sides. Here you don't have to say plus or minus because the radius is always positive. It is a length. Lengths cannot be negative. So the square root of 169 is 13. So we have r is equal to 13. So now we know what the opposite, the hypotenuse, and the adjacent side is, and we can find cos of alpha. So to find cos of alpha, remember, cos is speaking about ka in SOHCAHTOA, right? SOHCAHTOA. So it's the adjacent over the hypotenuse side. So let's look at what we have. The adjacent side, okay, if your reference angle is here, the adjacent side is the side that is next to the angle. So that's -5 over your hypotenuse, which is 13. So it means that cos of alpha is equal to -5 over 13. Okay, moving on to the next question. Okay, so then we have tan of 180 minus alpha. Grade 12s, don't get scared when you see this. This is a reduction. Just remember your reduction diagram. Okay, remember where 180 minus theta lies. That lies here in the second quadrant. And what is positive in the second quadrant? Sine. Sine is positive. So it means that tan is negative. So you're going to reduce this. It's in terms of alpha, which is perfect because we're working with alpha here. So when you reduce tan of 180 minus theta, because it is negative, it becomes negative tan of alpha. That's what we have there, okay? Because it falls under that quadrant. So just find out now what negative tan of alpha is. From SOHCAHTOA, tan says opposite over adjacent. So the opposite over the adjacent, which is negative 12 over negative 5. So remember that you still have a negative here. Then we're saying negative 12 over negative 5. And so you see that those will become positive together when they multiply. But then when this negative multiplies in, they become negative. So you end up with a negative 12 over 5 as your answer. Okay, moving on to the next question. Okay, question 3.2, we have a trig expression. We have to simplify this expression. So the first part that we have is the sine x minus 180 degrees. So look at that carefully. The reduction is supposed to say 180 degrees minus x, right? So it's not x minus 180 degrees. And the thing about this is that your angle is negative. You see that you have a negative 180 degrees. X is regarded as an acute angle. So even if you had that x minus the 180 degrees, your angle will still be negative. What you should do when your angles are negative is you need to add 360 degrees to that. Okay, so do you also see that here we also have an x minus 90 degrees? Same issue. Your angle is negative. So always focus on that number. If the number is negative, your angle is negative and you need to add 360. For this one, I'll talk about it separately. Okay, here as well, I'm also seeing negative angle. See, 360 is negative. So you need to add 360 degrees. And then this one is just a cofunction. So let's see. We're going to have sine of, if you add 360 degrees to negative 180, that's like saying 360 minus 180, which gives you, write the angle first. It gives you positive 180 degrees. And do you see that your x is still a positive x? Okay, it's not negative. Then you have this, and I said I'll speak about this one separately. This one has shown up in I think the two previous papers that I just did. That question, be very careful. I know that many grade 12s have a tendency to say, okay, I'm just going to take out a common factor of negative 1 and put it here. You need to be careful. This works for every other cofunction, like it works for the sine of x minus 90 degrees. It works for the sine of negative x minus 90 and even cos of negative x minus 90, but it will not work for this one. And that's why it's important to understand how this simplifies. So I will still put up the formulas of cofunctions up. So here they are. But you also need to know how to simplify it. So here is a method in which you can simplify it. You see, the angle is negative. So the rule is add 360 degrees to this. So now you're going to have cos of 360 minus 90 is 270 degrees. And your x is still positive. Then this is still cofunctions. So what we're going to do is we're going to remove a 90 degrees from this. So we're going to rewrite 270 degrees as 90 degrees plus 180 degrees. And then we still have plus x. Then it's like grouping these two together. So do you remember the cofunction that says, and I'm going to put it up here. Do you see that cofunction? Right? So if you know that cos of 90 degrees plus a simplifies to negative sine of a, then that's how that's going to simplify. You're just going to have to treat this a as if it's your 180 degrees plus x. So look at how we'll simplify that. It becomes negative sine of a, which is 180 degrees plus x. And then now you're going to reduce. You see that you have a negative first, but how do we reduce sine 180 plus x? Sine 180 plus x lies in so that part, 180 plus x, lies in the third quadrant, which is tan's quadrant. Sine is negative in tan's quadrant. So we have a negative outside, but this becomes negative sine of x. And you see now that when they multiply in, right, that will become positive sine x. That's why I said be careful with this one. So you can still study the cofunctions. Here they are again. You can take a screenshot and just make sure you remember about that one. That has come up a lot. So all in all, that one simplifies to sine of x. So we can just rewrite that there. So over here, we just have multiplied by sine x over. Here we're adding 360 because the angle is negative. So this is cos of, if you add 360 to negative 360, you get nothing. You get negative x. Okay. Now the thing is the angle is still negative. X is an angle. It represents an angle. So when the angle is negative, you can just add 360 degrees to it, right? So really your angle here is going to look like this. 360 degrees minus x. You just always add 360 until the angle becomes positive. Even if it's like negative 1080, keep adding 360 until it becomes positive. Okay, then we have this, which is a cofunction, and I've showed you how to reduce the cofunctions. Okay, so that is multiplied by, that becomes cos, positive cos of x. So that one does not change to negative. Okay, now look at what we have. We still have some reduction to do on top. You saw how sine 180 degrees plus x becomes negative sine of x because this is tangent quadrant. Sine is negative there. Multiplied by positive sine of x. And then we have cos 360 minus x. 360 minus x appears in cos's quadrant, and cos is positive in that quadrant, so this gets reduced to positive cos of x being multiplied by cos x. Okay, so you see what we have here is this negative being multiplied by this positive. It's just negative sine squared of x over cos squared of x. And this can get simplified too. We still have the negative, but do you remember the trig identity? Here are the trig identities. So if we know that tan of a is equal to sine a over cos a, then that means that this simplifies to negative tan squared of x. So that's our answer. And that's what that trig expression simplifies to. Okay, so we're on the last question now of this paper. So question 3.3, and it says, given cos of a minus b is equal to all of this. Okay, so this is the rule that we have. They say use the identity for cos of a minus b. So use this identity to derive an identity for sine a plus b. So you know what sine a plus b is supposed to be equal to, true? But we need to now use this rule that we used here to derive an identity for this one. So really what we're starting with is, in other words, we're really just trying to get this, right? Identity. We're trying to get this one's identity, what it's expanded to, that's sine a cos b plus cos a sine b. We're trying to get that by using the rules that was used here. So we're starting with sine of a plus b, right? Okay, so sine of a plus b is equal to, so the issue we're trying to get the identity for this by using these rules is that these rules have to do with cos. They say cos a minus b, but here we have a sine. So now we need to change the sine to a cos. The only way we can do that is by using cofunctions. So do you remember that the identity or the cofunction for sine of, let's say, x would be equal to cos of 90 degrees minus x. So we're going to change the sine of a plus b, but we're going to treat the a plus b as our single angle. And we're going to expand this by saying this is now equal to cos of 90 degrees minus, like here we have minus x, we're saying minus a plus b. Okay, so that's the first part. Now that we have this, we're going to distribute that negative into the bracket. So we have cos of, and let me even explain why, because I don't want it to just be a step-by-step thing. Here's why. You see, we're constantly trying to use this rule, right, on what we have here. The issue with this is that you just have a 90 degrees here, you have a minus, and then the a plus b is together. In this identity, right, do you see that cos a, cos b, the angles are separate, they're separated and alone. We need that to happen here. So what we're going to do is distribute into the brackets so that we can actually get a hold of each of the a and the b first. So this is what I mean by this. We say cos, and then we have 90 degrees minus A, and that also becomes a minus B. Okay, now that we have this, okay, so that we can have a situation of having cos of A on its own and cos of B on its own, what we're going to do is, because we have 90 degrees, it's a powerful thing that we can use. We can group 90 degrees and A together because of cofunctions. When we expand that as a cofunction, you know that you're going to have cos 90 minus A, and it can simplify to something of A, like sine of angle A. That's what we're trying to get. We're trying to get it to say cos A or sine A. Okay, but that angle needs to be alone with that function. So now that we have this, we have grouped these two together. Do you see now that the rule that we have here looks a lot like what we have here? Look at this part. It says cos of an angle minus another angle. That's what we have here. Cos of an angle minus another angle. So we're going to treat this one as if it's A, 90 minus A, that's A, and B as if it's B. And we're going to look at the expansion of that. So the expansion says we're going to have cos of A, meaning cos of our first angle, which is 90 minus A. So we have cos 90 degrees minus A. And then it says cos of B, meaning cos of our second angle, meaning cos of B. Then you see, when it has a minus, it changes its sign to a plus. We also have a minus, we'll change our sign to a plus. Then they have sine of A, meaning sine of whatever our first angle was, which was 90 minus A. Okay, minus A. And then they have sine of B, meaning sine of whatever our second angle was. So sine of, and here our second angle is just B. Okay, so now we just have to simplify our cofunctions. Cos of 90 minus A is equal to what? Remember the cofunctions? So cos of 90 minus A is equal to sine of A. And then we have cos B. Then we have plus sine of 90 minus A is equal to cos A. And then multiply by sine B. And there we go. We have used this, okay, we have used this rule to create an identity for sine A plus B. And that is why sine A plus B is equal to sine A cos B plus cos A sine B. Okay, so that is the end of this paper. I hope you guys enjoyed it. If you enjoyed this video, please make sure to leave a like and subscribe for more content like this. And I will see you guys in the future videos. Bye for now.